Good morning, everyone. I'm Reza Said Kandezi, and today we are going to talk about the precision testing for analog to digital converters, and we are going to use IEEE 1057 as the framework. Uh, in this discussion, we are going to talk about the ADC architecture, how we have to develop the testing configuration, and measurement techniques so we could make sure that we have a reliable and repeatable testing procedure and result. Now, before we start the discussion about the IEEE 1057, let's start with a fundamental question: why we care about the ADCs, the analog to digital converters? Well, ADCs are converting physical quantities like temperature, vibration, or audio into the digital system. The quality of your ADC basically this mandate the integrity of your entire system. Without them, we don't have a signal processing, we don't have an automation, and we don't have a feedback system in our engineering system. Basically, DC signals are, we can consider them as the backbone of physical measurement. They are constant, so not time varying signals. And ADC convert these constant voltages, analog levels, into the digital codes. Okay, so we have DC signal, constant signal, that ADCs convert them into and translate them into the digital codes. Okay. In this procedure, precision matters because any offset, any drift, or any gain error could affect the result, and normally they are sensitive to the environmental condition too. Now, DC measurement basically anchor the low frequency and steady state behavior. Okay, so they are serving as a reference point. Now, the DC testing, which we call it static performance characterization, and we're going to discuss that later on, emphasize that the primary concern with how accurately the ADC responds to the DC inputs. We have key parameters on that, like offset error, gain error, or INL and DNL, which we are going to go through these factors, and we are going to have a case study over them. And basically, in an inaccurate DC behavior in ADC can lead to incorrect measurement. Okay, especially when we talk about precision calibration, and that precision calibration is a requirement, like for example in metrology, power system, or biomedical applications. Okay. Uh, Now, why IEEE matters? IEEE 1057 matters for DC. Different, basically, DC architecture has significantly different behaviors. We have SAR, which is successive approximation. We have sigma delta. We have pipeline. We have dual slope flash. All these architecture has their own unique sensitivity to errors like linearity distortion or timing jitter. Therefore, testing of the ADC must go beyond the architecture. So we have to consider reference voltage stability or input signal or clock accuracy. So, and environmental factor, because temperature or like ground noise also significantly affect the performance of these testing and the ADC behavior. Okay. Uh, but before IEEE 1057, uh, vendors use their own terms and instrument and procedures. So that uh, variation between the vendor's definition, assumption, and description basically made the confusion and cause a misleading in a specifications. Okay, so IEEE 1057 started was introduced to actually eliminate this inconsistency. So we define parameters like INL, DNL, THD, and we set some protocols for testing the ADC. These standards recommend how we could have a test setup configuration, how we have to apply calibration, and how we have to document the result. Okay, without this standard, basically manufacturing facilities, the vendors, could exaggerate the specs, okay, because they would implement their own assumption or their own testing configuration that favors their result and their product. So IEEE 1057 basically enforces an engineering accountability, okay, and links the measurement precision with universally accepted kind of like condition and terminology. And together, all these together would actually guarantee that ADC testing is credible and reproducible, and we could trust these results that come up out of these testing defined by IEEE 1057. Now, let's talk about the history and legal motivation. Okay, why actually the industry got motivated to develop such a standard. As we said before, IEEE 57, each vendor has their own testing setup and definition, so it makes an unverified performance kind of like claims. Okay, so it was inconsistent testing condition, and each of them has some like a dangerous assumption. Okay, in their process that, as we said, it would favor them. So IEEE 1057 basically brought a legal and engineering alignment. It's actually protect you and the customers. And also the regulators. So with that, if you meet the IEEE 1057 requirement, basically it means that you achieve the full and you followed your full responsibility. Okay, and but if you fail or if you don't follow the IEEE 1057, if there is any inconsistency, if there is any problem, then you are responsible legally and technically for those inaccuracies. Now, why we need that? Why it matters? Okay, uh, why we have to like talk about this standard is not just learning the standards. You actually have to try to come up with a standard of the thinking. Okay, so this is an example. You need to like specify the procedure and parameters accurately, measure responsibility, and document professionally. Okay, now as we said, ADCs has different architecture, okay, and each architecture has their own unique sensitivity to the parameters and significantly different behavior and performances. Okay, so some ADCs are optimized for a higher speed application like flash or pipeline. Okay, in these architecture, sampling rate and signal to noise ratio are critical. Okay, other architecture like Sigma Delta mostly focus on resolution and noise shaping. Okay, so they are most suitable for low frequency and high accuracy system like audio or instrumentation. Okay. Uh, in power system and energy metering, the emphasis of the ADC behavior is in linearity and offset accuracy, as well as temperature stability. So then in this kind of like application, SAR kicks in, okay, as a suitable ADC architecture. Okay. So this diversity shows that no signal metering or setup can fully capture the performance of all IDC across all applications. So what matters is one system may be irrelevant in another aspect. So each each use case brings a different combination of the signal characteristics, resolution need, speed requirement, and environmental condition. But despite this variation, all ADCs must be tested and compared under common framework. Okay, this way we can trust and have an interoperability across the industry. So now IEEE 1057 kicks in and plays a critical role. It provides a modular and scalable testing methodology that can be adopted to various different ADC types and architecture. So this standard actually support this diversity and defines a universal metrics and defines a universal and clear testing procedures uh, and categorize them in static and dynamic testing. We are going to go through this static and dynamic testing too. These standards actually accommodate the different signal type, clocking modes, or interfaces and environmental conditions while preserving a methodological rigor. Okay, so we would have a uniform evaluation for the different type of ADCs. These different architecture basically has a different characteristics. So like SAR normally has a resolution of 10 to 16 bits. Okay, and the speed of these SAR could go up to tens of mega sample per second. So these combination of the parameters make them suitable for industrial sensor power monitoring. In the other hand, sigma delta has a higher resolution, as you can see, 16 to 24 bits. Uh, but the speed, kind of like it's a trade-off. The speed is gonna be reduced to a kilohertz or to a low megahertz. So this one, because of the resolution, is good for audio recording or instrumentation. Okay, or for example, the flash architecture has a relatively lower resolutions, but the speed is up to like 1 to 4 gigasample per second, which because of the speed, we have the speed of sampling, we have it makes the flash architecture very suitable for higher speed oscilloscopes and radar systems. So you see that how the architecture and its characteristics actually make a difference in the performance and make each of these architectures suitable for different application. Now, IEEE 1057 was, as we said, was designed to support a broad range of ADC. Okay, this standard does not limit itself to a specific industrial kind of like or application, industry or application. Okay, IEEE provides this IEEE 57 provides the flexibility needed to test the ADCs for performance classes, sampling rates, and resolution level. Okay. IEEE 1057 is actually intentionally has a modular in a structure. It has a modular in a structure. Okay, so this modularity actually allows engineer to select and apply only the relevant part of these standards. Okay, for example, it goes to if the goal is to verify offset and linearity, one may only apply the static test. But if the focus is on spectral performance and high-speed ADCs, then dynamic testing section is applied to our procedures. Now, how these testing configuration dimensions differ? The tests differ in the different kind of like setting and condition for different ADC architecture. So testing an ADC is not just about applying a signal and reading the output. It involves many careful control dimensions. Okay, so this standard defines several configuration dimensions. Okay, so it would have a structure that defines how ADC is tested and under what diverse condition this test would be conducted. So each dimension impacts measurement accuracy or repeatability or and relevance, especially when comparing different ADC architecture. Okay, so the first dimension in this testing is type of input signal. Different signal type like DC ramp, DC step, sinusoidal, two-tone, or impulse response are going to be used in testing the ADCs. Like DC ramps and step are used normally for static testing. Okay, and sine waves or two-tone signals are normally used for dynamic testing. Okay, or like impulse response are useful for analyzing settling time or overshoot and frequency domain responses. Okay. Beside the input signals, the second dimension is the sampling mode. Okay, which basically is defined based on how the ADC samples the input signals. Okay, the IEEE 1057 supports multiple sampling configuration. Okay, so it could be internally clocked, it could be externally clocked, it could be synchronous, it could be asynchronous. So like for example, in internal clock, the ADC uses its own sampling clock, which basically limits the control but simplifies the integration. But if you use external clocking, it allows a precise timing and control and synchronization with the signal source. Okay, which if we wanted to like have a coherent sampling, it's very critical. Now, synchronous sampling means basically the input signal and sampling clock are phase locked and actually frequency locked. But in asynchronous sampling, there is no fixed phase relation between the signal and the clock, which basically may be representative of the real world condition. Okay, but it's very harder to analyze. Okay, and have a precise analysis on these test results. Now, the third dimension is measurement interface, which refers to how the output of the ADC is accessed and processed during the testing. Some ADC provide digital data output via like interface like SPI, LVDS, or like parallel buses, which basically captures directly using a data acquisition tool. Okay. Other test setup can use the analog reconstruction. So the ADC output also pass through a DAC module that again change the digital signals to an analog signal, and which normally is used in analog instrumentation. But the choice depends on the type of ADC and the resolution and the bandwidth of interest. Okay. Now, the fourth dimension is environmental control. Okay. So basically, it refers to how external test conditions are managed to prevent them from interfering the result. Okay. So key factors is temperature stability, power supply regulation, electromagnetic shielding, or clock condition. Okay, because even like a small change in temperature can introduce an offset drift. Okay, or unregulated or noisy power supply can create ripples which induce distortion. Okay, EMI or electromagnetic interference can corrupt the signal integrity. So it basically creates a false nonlinearity. And clock conditions ensures that the timing reference used in sampling is clean and with a low jitter. Okay, so it's specifically in dynamic testing is very important. Now, IEEE 1057 actually provide this guidance for all these dimensions, and the tests are to make sure the tests are realistic and controlled. Okay. Now let's talk about we introduced and we use the word static testing and dynamic testing. Let's see what are the parameters that we define in static testing for ADC testing. Okay, so uh, in a statics testing, we actually evaluate how accurate the converter responds to a slow changing signals. Okay, these parameters basically are important for understanding the ADC's transfer function or linearity and the behavior near code transition. Okay, static testing are commonly performed using a DC ramp input, which slowly increased across a full input range. Okay, the first parameter in static testing is offset error. The offset error, we define it as a difference between the actual transition voltage from the first code and the ideal transition point. Basically, it shows a DC shift across the entire ADC output. Okay, so the curve of this transformation from the analog signal and the digital codes, if it shifts up or down, that means we have an offset error. Even if ADC is perfectly linear, a large offset basically misleads the transformation of the analog to digital codes. Next parameter is gain error. The gain error happen when the slope of ADC output deviate from the ideal slope. Okay, that means the ADC may convert a full scale input into a smaller or larger digital range. Okay, so basically it causes compression or expansion of the full scale. Third parameter is differential nonlinearity or DNL. The DNL measures the deviation of each actual code width from the ideal one LSB. LSB is short for least significant bit. Okay, if we have a deviation on each step, okay, on each code, then we have a DNL. If DNL is less than minus 1 LSB, then the ADC basically missing some codes. Okay, a good ADC maintain the DNL within plus and minus 1 LSB. Okay, so another factor is integral nonlinearity or INL. The INL defines as the deviation of the ADC actual transfer function from the ideal straight line. Okay, DNL, let's makes clear that what is the difference of INL and DNL. DNL focus on local step accuracy, but INL measures the global curvature or drift of the ADC response across the full input range. So DNL is local, INL is global kind of like parameters. The high INL actually degrade the absolute accuracy and are especially important when we talk about the measurement and instrumentation application. Okay, now these static parameters are typically calculated using a code density test or histogram methods. Uh, we have an input as a ramped slowly using a precise DAC, and thousands of samples are collected at each input level, so we can build a histogram. The shape and the distribution of the histogram are analyzed to compare offset, gain, DNL, and INL values. Okay, basically they give insight into the absolute accuracy, linearity, and monotonicity, which are critical in control system or like digital voltmeters or calibration grade instrument. Now, we talked about the static testing. Let's talk about the dynamic parameters. Uh, we said that the static parameters analyze the ADC's behavior with slowly varying input. But on the contrary, the dynamic parameters measure how well an ADC performs when we have a rapidly changing signals, like sine wave or modulated inputs. Okay, so these tests mostly focus on the frequency domain behavior. The dynamic is mostly focused on frequency domain behavior and basically defines how ADC handles distortions or noise and interference under kind of like real-time sampling conditions. The first dynamic parameter is SNR or signal to noise ratio. This ratio is the ratio of the power of the fundamental input signal, which is your desired frequency, to the power of all non-harmonic noise components. Pay attention, all non-harmonic noise components. It's typically measured in decibel and shows how clearly the ADC can separate a clean signal from a background noise. Okay, like high SNR means better resolution and less random noise in digital output. The next parameter is THD or total harmonic distortion. This parameter actually quantify how much harmonic content is appear in ADC output. It measures by comparing the power in all harmonic frequencies, like second, third, up to infinity, to the power of the fundamental signals. The fundamental signals is the frequency that you desire. Okay. Low THD means ADC introduce minimal nonlinearity distortion, which basically is very important in audio communication and signal fidelity applications. Uh, Next parameter that we wanted to like discuss is SFDR. It's a ratio of the power of the fundamental signal to the power of the largest frequency component. Okay, spurs can arise from harmonic distortion or clock feed through or crosstalk or digital switching noises. This parameter defines that how ADC defines the ADC's kind of like ability to resolve weak signals in the presence of a strong tones and is very important in radar, wireless system, and spectrum analysis. We have a signal to noise distortion rate ratio. It's ISINAD, which basically includes this parameter includes both noise and harmonic distortion. Okay, it's a more comprehensive picture of the SNR alone. Okay, it basically show the total undesired content in the output and is a key indicator of overall dynamic fidelity. Now we have several other factors like effective number of bits uh, or using the fast Fourier transform. We could analyze the signal frequency domain. All these are within the dynamic testing. Now, what are the differences between static and dynamic testing and why we have these two categories? Uh, each method, static and dynamic, actually evaluate different performance aspects, and they are necessary to fully understand how the ADC behave in various conditions. Okay, so neither is sufficient on its own, so both are kind of like complementary. Okay, the static testing, as we said, is testing the ADC's behavior when we have a input signal which is a steady or changes very slowly, like DC ramp, DC steps, low frequency waveform. Uh, this type of testing focus on accuracy and linearity. Okay. On the other hand, the dynamic testing evaluate the ADC under rapidly changing input. Okay, so like sine waves, two-tone signals, we already talked about that. Dynamic tests mostly focus on how ADC handles noise, distortion, or frequency domain integrity. Okay, so the difference in this methodology is significant. Static tests often use code histogram, okay, and look at ADC's behavior over time. For slow input, dynamic tests use spectral analysis and require large sample sets. Okay, the equipment setup and the signal requirement are also different, which it is obvious. Static testing emphasizes DC precision, while dynamic testing require low jitter clock and basically spectrally pure sine waves. These two types also uncover different kind of faults. Okay, static testing reveal missing codes, offset drift, or gain error, while dynamic testing is basically to detect the harmonic distortion or jitter effect. So static and dynamic testing are not interchangeable. They serve for different purposes, and together they kind of like provide a holistic view of ADC's behavior. Now, let's talk about how we could how we could design and complaint test based on the IEEE 1057. Uh, Designing a test actually requires more than just connecting a signal to the ADC and reading the output. It's not just like that. It begins with a well-defined plan, okay, that basically makes sure that each part of this test is controlled, like signal, setup, capture, analysis, and they are traceable, okay? The first step, we need to define the test objective. That means we have to identify the device under the test or DUT. Okay, for example, it could be a 12-bit SAR ADC operating at 500 kilosamples per second. Okay, these parameters may include the static meters. Okay, we define based on that we define the performance metrics, and these metrics includes static metrics like INL or DNL, or it could be a dynamic noise that we have to like evaluate. Knowing the objective actually allow us to select the appropriate testing signals or appropriate equipment. You must create after that, you must create a system block diagram. Okay, this diagram shows a map of the full signal path from the signal generator through the buffer, through the ADC, and finally the measurement or data capture system. It should include the reference voltage source or clock signals or isolating barriers and a clear block diagram. Basically, make sure we understand every stage where noise, distortion, or delay can be introduced into our performance of the ADC or testing result. When we have the map or the block diagram, then we need to configure a test signal source. Okay, for static testing, we use a high resolution DAC processing a clean ramp or step waveform. For dynamic testing, we use a precision sine wave generator with low THD, typically below minus 80 decibel. So after you define the signal source, you develop a detailed test plans. Okay. Like for example, static testing includes a DC ramp capturing output codes, constructing a histogram, and calculating DNL and INL offset and gain errors. Or dynamic testing includes applying a coherent sine wave, collecting output samples, okay, applying FFT and calculating like THD or SNR or all those things. Now, this IEEE 1057 basically incorporate environmental condition and calibration too. Okay, so the temperature of the test setup should remain stable because the difference in temperature will affect the test result. On the other hand, all the test instruments must be calibrated. Okay, so we know that they are accurate, and we have the uncertainty of each step of the measurement, each range of the measurement for each instrument in hand. So we could actually analyze and we could identify the errors introduced by the testing instrument that we use. Okay, so we could separate the actual errors in ADC and the errors that we introduce into the test. Now, in static testing procedures, okay, we apply a ramp signal, we record the output as we said, we construct the histogram, and we perform metrics. In dynamic testing, we apply a coherent sine wave. We capture the ADC output samples, we calculate the performance metrics, and we capture the output, we perform an FFT, and then we calculate the performance metric. Now let's go through a case study and see how actually this system, how we could like define this system as a how we could run these tests, static tests and dynamic tests, for example of like a SAR ADC. Like the specific model is the ADS 7042 in this uh, case study, which is built by Texas Instrument. Okay, basically this case study defines or shows that how an ADC is tested using IEEE 1057. As we said, the first step is to identify the device under test, which in this case is the 12-bit SAR ADC with the specified model, the Texas Instrument ADS 7042. This ADC, this specific ADC operates as a medium speed, and is commonly used in industrial sensing or monitoring application. The test setup should include a precision signal generator. We define that the setup after that. We remember we talked about that. The precision signal generator, a unity gain buffer, an anti-aliasing filter, and a USB-based data capture interface. So now we have our testing setup. The signal generator will produce both DC ramp and a sine wave because we wanted to like have the static and dynamic testing. And the buffer isolate the generator from the ADC loading effect. So basically filter ensures the high frequency noise does not lies into the ADC's bandwidth. In static testing, we apply a DC ramp, okay, across the full input system, and the output will be captured and used to generate a histogram for linearity analysis. When we run this test on the specific ADC that we mentioned, we measure different static parameters like INL. In this case, the INL measured is 1.8 LSB, which is within the specified limit of 2 LSB. So this ADC actually passed this parameter. The DNL measured for the result basically is 0.95 LSB, which is also under the limit. We said that the limit should be between minus 1 and plus 1 LSB. So 0.95 is uh, less than that, so it means that we don't miss any codes. We measured the offset errors and it was 0.6 LSB, and the gain error was 1.1 LSB. These are both comfortably within their limits, which is 1 and 2, okay? And the result confirmed that ADS actually behave accurately and meets all the specification and criteria for static testing. Now, in dynamic testing, we apply a sine wave and sample at a frequency aligned with the ADC sampling rate. We run an FFT spectral analysis, and we measure the parameters that are important for us, like effective number of beats. This measure, like for this specific model, was 11, which is slightly lower than the typical value of 11.3. Okay. The SFDR measured for this specific one was 85.1. Okay, which basically exceeds the specification of 80, indicating that has a excellent spectral purity. Now, this small drop in ENAOB, the effective number of bits, basically shows that elevated electromagnetic interference in the lab environment. Okay, it shows the importance of the environmental control. If we have a more controlled environment, that parameter would likely meet or exceed the typical value. So this case study basically validate the utility of IEEE 1057 and provides a scientific, structured, and repeatable testing. Okay, it shows how static and dynamic tests together give a complete picture of ADC behavior. So how do we set up the test? Let's go deeper into that. So far, we talked about the general idea of this case study. Now, for test setup, as we said, we have different equipment like signal generator, utility gain buffer, anti-aliasing filter, the ADC itself, the data capture interface, and oscilloscope that bring us the histogram. Uh, when you wanna to like do the test, what's important, as we said, is temperature is one of the important parameters. So, and we know when the electrical system works, the temperature rise happen because of the losses. So before we measure, we need to let the temperature stabilize. So the system warm up. Like it takes approximately 30 minutes, but you need to like make sure that the temperature is stabilized. The definition of the stabilized temperature is when the temperature actually varies or increases less than 1 degree Celsius in 1 hour. If we have such a slow uh, uh, temperature rise, then we basically can say that the temperature is stabilized. Now we have to use a metal box to reduce EMI. You already see in the result that EMI basically uh, made a effect on the ENOB parameter. So we run the test, statics test system, measuring accuracy, linearity, and code behavior. We run a dynamic to measure the distortion, noise, and frequency domain behavior. In a static test, we apply a slowly increasing voltage ramp, like for example, from zero, in this case, from 0 to 3.3 volt. Okay. Then we record the digital codes that are output of the ADC. Okay. That INL, as we said, defines how far ADC output is from the perfect strain line. This one passed the limit, so the nonlinearity in the output is within the acceptable limit. The DNL defines how output steps are basically have the same size. Each step, okay, has the same size. Again, we pass this test because the limit is plus minus 1 and we are in the range. The offset error shows that the whole output if shifted up or down. So we have zero point 0.6 LSB, meaning it's shifted up uh, 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 making the effect of zero point 0.6 on the LSB difference of the zero point 0.6 LSB, but the pass limit is 1, so we are okay. We don't miss any code. The gain error shows how the slope is changing. Okay, so it's 1.1 LSB. The limit is 2, so it shows that we have a steeper, kind of like a slope in our transfer function from analog to digital codes in the system. So it means that the ADC faithfully reproduce the analog voltage to as the digital values. It does not skip any codes. It has a clean linear transfer functions and is well behaved. Okay, so this is what we've done and what it means in this case study for static testing. In dynamic testing, let's go a little bit deeper. We apply a pure sine at the frequency that is mathematically matched to the sampling rate. Okay, and then we use the FFT to see how it prevent the leakage or the distortions. The effective number of bits shows the real world resolution. Okay, so real world resolution, not ideal, theoretical. And it includes noise and distortions. So when we have 11 bits, and the typical value is 11.3, it's tell us that this specific ADC behave closely like an ideal when there is a noise or distortion, but it has a slightly kind of like differ from the ideal case. Now in SFDR, we basically define the distance between the main tone and the worst spirit. The acceptable limit is should be bigger than 80 decibel, and what we measured is 85.1. So it's excellent. So the largest spirit is lower than the main tone. So this is the result. Now, the only problem that we observed, as we said, is the ENOB is slightly worse than the datasheet. We talk about that the root cause could be AMI in the lab, okay, or USB noise, switching power supplies, or unshielded kind of like laptop, or it could be after testing in a more isolated environment. We can actually improve this parameter. Now, there are several challenges when we talk about the real world testing challenge. Even when we follow the IEEE 57, the real world testing still face several practical challenges. This challenge basically is caused by the factors that are beyond the standards. Okay, we have to understand these factors, the physical, electrical, and environmental limitations, and try to mitigate these issues. Okay, the first major challenge is temperature stability. We already talked about that during a typical test session. Room temperature can fluctuate. Okay, so this temperature drift affects both ADC and the test instrument. Okay, so in that case, in the document, we have to mention that this point, like for example, minus plus 3 degree changes over the 3 hours actually caused zero point 0.5, like for example, LSP swing. Uh, this kind of drift, as you know, as you could understand, is basically affect the DNL-INL, or it could the measurement that we have, or the gain error is not gonna be accountable, the one that we got from the measurement. But to address this issue, we have to have a temperature control chamber to reduce the time variation, the temperature variation, and we reduce the effect of this variation into our result. Another challenge that we have is the grounding issue. Okay, particularly in USB-based test setup, when multiple instruments basically share a common ground, okay, the ground loops are created. These loops introduce unwanted current and common mode noise. Okay, in the case study that we have, a poor grounding led to inconsistent static measurement. The solution is we are going to have to use a USB isolation hardware that basically implementing a star ground configuration when all the grounds connected to a single reference point. This minimizes the uh, noises and the grounding loop effect. The third real-world challenge is software configuration, particularly the FFT-based testing. Okay, a common mistake is selecting the wrong window function for spectral analysis. A rectangular window normally is used. For example, in the test that we have, the case study, which may cause a spectral leakage. So it would end up in an inaccurate reading of the harmonic distortion. When we switch to the Blackman-Harris window, which has a better side lobe suppression, then it become more accurate and the measure metrics matched expectations. This example actually shows that even the best hardware and the most perfect methods can also fail without attention to the real world challenge. Uh, EMI from nearby equipment, you have like your cell phone in hand or another like EMI sources. The clock jitter or unshielded cables, they could introduce artifacts. Okay, now, so we have to make sure that we are aware of this challenge and we try to mitigate or reduce the effect that this challenge could make into our output result. Now, IEEE 1057 is not the only the standards that applies to this ADC. They are an ecosystem of standards that help us to have a better, precise testing system. The IEEE 1241 is the expanded ADC testing and focus on modeling and calibration of the highest speed ADCs. Okay, and it's recommended for the cases beyond the IEEE scope, IEEE 1057 scope. The IEEE 1139 talk about the signal generation. Okay, it covers the single tone sinusoidal signal and is essential for setting a high purity signal. Okay, when we talk about the dynamic test and FFT based test. So this is very important to ensure the standard compliant. Okay, IEEE 1159 is another IEEE in the standard in the ecosystem of ADC testing, which refers in the power quality and that applies to ADC-based waveform logging and defines events like sags and harmonics in the power system. IEEE 4051 discuss about the smart sensors. Okay, and it's used when the ADCs are integrated into the modular sensor network. Okay, so this is important to make sure that we know what are the complementary standards are for the IEEE 1057, and we might need to apply those standards too. Now, IEEE 1057 is a powerful standard, okay, but its real strength emerge when understand as a part of a broader ecosystem. We talk about that. So this standard is more than just a technical document. It actually gives us a framework for engineering excellency. It teaches engineer not only how to test ADC, but how to think and communicate in the precise, rigorous, and professional way. By mastering these standards, we can learn to apply exact definitions or reproducible methods and follow evidence-based reasoning. Okay. Uh, Applying these standards also develop a systemic thinking. Okay. Another benefit of this standard is interdisciplinary collaboration. It defines the common terms and expectation, and it allows analog designers to test engineers, framework developer, and auditor to all communicate using a shared technical language. But perhaps the most important aspect of that is teach us ethical engineering practice. Okay. It could affect the safety critical decisions, compliance certification, and legal contract. Okay. This mindset actually carries forward into the every aspect of the professional work. These are the qualities that define excellence, not just ADC testing. Thank you for your attention. If you have any question, let me know and have a good rest of the day.